So today we're gonna cover geometry and then computational geometry. So first let's go over the basics and definitions. We can represent points by a pair of numbers, x and y, and we can represent vectors in the same way. And if we just think of points as vectors, it allows us to do many things. So the simplest operation which we have is addition. We can add two vectors, and you'll just get the sum of the x coordinates with the sum of the y coordinates. So adding these together, you end up with the green vector. Subtraction, defined similarly, you subtract the latter x value from the former x value, and you subtract the latter y value from the former y value. So if we subtract these two, now we're subtracting v from u. So here's some simple code which accomplishes this. We overwrite the plus operator here and the subtraction operator. You could of course just do this with a function. What we can also do is we can use the complex class. So that's a class for complex numbers, and we define we want double precision here. And the complex class, which can be found in C++ and Java and probably Python as well, but I don't know. And then it's just dependent on the standard library, whether they include it or not. It usually comes with support for these operations: an addition, subtraction, multiplication by a scalar, so with a single number, some way of getting the length, and also support for the trigonometric functions. Complex numbers have a real part and an imaginary part, and we can think of this as vectors on the complex plane. So the real part is your x value, and the imaginary part is your y value. So we can, in C++, we can call the function real to get the x value, and we can call emag to get the y value. Then we have the function abs. This will return the length of the vector. We have the trigonometric functions, sin, cos, and tan. For lines and line segments, we represent them with a pair of points. So these are any 2 points, as long as they're not equal, will uniquely define a line for us. And the distance between the 2 points is the length of the line segment, or just the vector between them. So to find the distance between the points, just subtract one of the vectors from one of the points from the other to get the vector, and then find this length. So if we use our point structure, this will look something like this. Here we define a default value of the origin. So if you call the distance function without a parameter, it'll give you the distance from the origin. We can also just use the apps function with our complex class. Now if you want lines, we represent them the same way as line segments. We just have to know that they are infinite and not bounded by the points. So we just treat them here as lines that pass through the points. You can also just store them as a starting point and a direction vector with some length. Or you can normalize the direction vector, and then you just have a point and a direction. So your direction vector will be of length 1. Whichever way you take, you'll have a pair of 2 points. It's also quite easy to represent circles.
So the t in the previous was what, like the magnitude of the direction vector, or?
Yeah, so here we have our point, and then if you subtract this point from the other one, then you get the vector here, and it has a magnitude and a direction. So the t here is the magnitude, and the r is the direction vector. So usually what you do is you just take this vector and you would normalize it so it is of length 0, and then you store the starting point and the direction vector.
And the magnitude, I suppose, if necessary.
Yeah, but if you have a line and not a line segment, then you don't need the magnitude because your line is infinite.
I see.
However, if you have a segment, you would need to store the magnitude to know where to end.
Right, so you have P, which is your 2 points. Then you would normalize R just so you have a direction vector.
Yeah.
And then you can always calculate T as needed.
Yeah, you could calculate, you have P0, you calculate the other P here. Personally, with line segments, I think just using the 2 points is better. With lines, it can vary. Yeah, we can represent circles easily. We have the center point, and then we have a radius. So this is just a pair of point and double. And as with lines, when we have 2 points, given that they're not equal, they will uniquely give us a line. If you have 3 points, which are not collinear, so they are not all on the same line, this will uniquely define a circle. The dot product is one of the operations you will probably use a lot in geometry. So given 2 vectors, we define the dot product as the termwise product or the sum of the termwise products. So we have x0 times x1 plus y0 times y1. And if this was a 3D vector, you would continue z0 times z1 and add that. In geometric terms, this is the magnitude of the u vector times the magnitude of the v vector multiplied with the cosine of the angle between them. So if we take the dot product of u and v and we divide it by the magnitude of both vectors, we can use the inverse cos function, arccos, to obtain the angle. We can also get the projection of v onto u. So then you take the dot product, you divide it by the magnitude of u squared, and then you get some scalar value, which you multiply with u, and then you reach some certain point here on the vector u, depending on how far along this v vector is. So if we go further here, we'll go straight down into this point. If we go even further, we'll go straight down onto this point. And this also gives us the closest point, because the closest point here to P on the line of U is going to be just straight down. So we can get this point Q in this manner. The distance from point P to the line is therefore going to be the distance from P to Q. Of course, you could say that you'd go another way, but that's going to be longer, and usually you want the shortest way to the line. Now, of course, we could have a longer vector here for v. So we go all the way up here. And then if this u is a line segment, then the closest point is going to be the end point here, because our point q is going to be outside the segment. So we're going to be using the complex class from now on. And as a shorthand, we made some definitions for points. So P of P is just saying we have const point reference to the variable name, which is put here in. So this here stands for const point reference A. Similarly for lines, we just make lines be pairs of points. So L of P0 and P1 just transforms into 2 points. So here we have the dot product, and we can call that for the angle. And then to find the closest point, we first need to check, is it a segment? and then this handles the two cases. Otherwise, it's just on the line segment, and we use the projection to find the point.
Sorry, your two cases were what again?
This is the cases for the endpoints. So when the vector here, when it exceeds the length of the line segment here. So we go all the way up here, and we're always going to go straight down to the vector. Maybe that's misleading. Not straight down. So you could imagine that u is rotated in a different way, and v is rotated in a different way as well. And you're going to take the shortest path straight down to, or straight to u.
And so maybe, so it's clear, u is what exactly? It's just some line segment beyond VU, or?
Can you say that again?
Like, what exactly is u here?
U is a vector, so from this point to this point.
I see. And so what is VU then?
V is a vector here when we were doing the angle, but now we're thinking of it as a point. So if you have the point here P, you would get the projection, and that would take you straight down here to the line segment. And the cases we're handling here is the case when we are
what I meant is you have a blue segment and a yellow or an orange segment. Like, what is the relationship?
Yeah, the blue segment is the projected vector. So you want to project this vector here onto this vector, and then you get this path from P to Q, and if you consider the length of this vector in relation to the length of the u vector, you see you are canceling the y value here. So you only get the x value of v. However, this also works if u is not just going straight, up on the x value. If you rotate it, it's gonna work the same way. V is gonna have the same direction as u, but it's.
So I guess what I mean is V like overlapping? Like is it rather like is it covering up part of U? Like do both V and U start at the sort of the same place?
Yeah, V and U start at the same place.
I see, and so this blue line segment is just covering up a part of U.
Yeah.
Okay. All right.
So U started like this, and then we did a projection, and we got V projected onto U. So here we're just calculating to see if the scalar would take us past this point or past the starting point here. We also have the cross product. So here we multiply the first x value with the second y value and subtract the first y value multiplied with the first y value multiplied with the second x value. So you have x0 times y1 minus y0 times x1. And we can write this in geometric terms as well. So we have the cross product of u and v is equal to the magnitude of the vectors multiplied together times the sine of the angle between them. So for dot product it was cos, the cosine. For cross product it's the sine. And this allows us to calculate the area of the triangle which is formed by these vectors. So consider the vectors u and v in the picture here. They form a triangle like so. The area is going to be the cross product divided by 2. It can also tell us if the angle is positive or negative. So if we have u cross v is less than 0, that means the angle is negative. If it's 0, then the lines or the vectors are collinear. If it's greater than 0, then the angle is positive. And this here can be very useful for many things. For example, clockwise or counterclockwise order. So, given 3 points, we want to know if the angle they form is a counterclockwise order. A counterclockwise angle in the order A, B, C. So, consider from A we go to B and then we go to C. This here is a counterclockwise order. A counterclockwise angle, sorry. Because when you follow along A, you take a counterclockwise turn and then go to C. And wait a minute. The B minus C, B minus A. Sorry, this should be C minus B and B minus A. And the arrow here is off. It should be at the other end. Because we're going from A to B and then from B to C. But the idea is the same. So we examine whether the cross product is positive or negative, or maybe it's 0. And this will tell us if it is a counterclockwise or a clockwise angle. If the cross product is positive, then it is counterclockwise. If it is negative, it is clockwise. So if you flip it around, if you go from C to B to A, then you take a clockwise turn. The value would therefore be negative. And in the case of 0, the points are on the same line. The 3 points are collinear. So we can calculate the cross product. We can use the cross product to calculate the area of the triangle and whether the angle formed is counterclockwise or clockwise. And we can also check if 3 points are collinear. A very common task we have is doing some intersections of lines. So we want to find the points where they intersect, or just whether they intersect, and we could have lines, or we could have line segments. We could have one line and one line segment. It can mix in anyway. So given a pair of points which represent a line, we want to get them in the standard equation form. So a times x plus b times y equals c. And you can do this by setting a to the difference between the y values, b to the difference between the x values, but the other way around. So here we subtract y0 from y1, and here we subtract x1 from x0. And then you set c to a times x0, and you set and add b times y0, y1. And if you have two equations like this, so you have two lines, you find the equations, you just need to solve for x and y. So we have these two equations, and if you go through solving this set of equations, you will find that x is equal to this expression here, y is equal to this expression here, where d has this value. So a similar problem we have is the intersections of two circles. So we have a couple of cases here. If the distance between the centers of the circles is 0, and their radiuses are equal, then these circles are equivalent. So they intersect all around. We also have a case where the distance between them plus the smaller radius is less than the larger radius. That means that this circle here, the smaller one, is contained in the larger one. So you take the distance plus the radius of the smaller circle, and that cannot reach the size of the larger radius. So it doesn't reach the edge here. And you can denote this in this way. D is less than the absolute difference of two radiuses, radii. You also have the case where the distance is greater than the sum of the radii. And then the circles cannot intersect because they're too far apart. So let's look at this last case where we have an intersection. So they're gonna intersect at distance radius a from point A and distance radius b from point B. And you see it happens in two places. Of course, if you pull them a bit apart, they could become tangent with each other. So they just slightly touch at a single point. Okay, so if we split this into vectors a and b here, and then we need the height up to the point that they intersect at. So we can solve for the vectors a and h from these equations. we have the equation that a squared plus h squared is equal to the radius of a squared. We have that b squared plus h squared is equal to the radius of b squared. This is just the Pythagorean theorem. Okay, so what we get for a is this expression. And then, since we know the radius of the circle A, we can calculate h from this equation here using Pythagorean theorem. And this is how it looks in code. So here I believe I ignored the case of equal circles. Yeah, so here we have the case where the circles are too far apart. And here we have the case where one is contained in the other. Both of these return 0 intersection points. Otherwise, we calculate the values for a and h. And then using these values, we find the point v. Sorry, the vector v. This is a vector v because we want to find the vector from a here to this point here. And then we find the vector from this point to this point. That's the vector u. And then we take the point by adding u. So we start at A, add V to get to the center. Then we add U to go up. And then we do another point where we subtract U to go down. Of course, this could be rotated in some way. So it's not necessarily up or down. It's just up or down in this picture. If U is very small, then the difference between these points is going to be very small. So we say that the circles are just tangent to each other. They're just touching. So there's just one intersection point. Otherwise, there are two. Okay, so then we have computational geometry, where we have some more complicated geometry algorithms. Let's look at polygons first. So polygons are just represented by a list of points in a specific order, which represents the edges. To clarify on that, so you would have this point in the list, and then next you have this point, and then this point, and this point, then this point, then this point, then this point, and that's your whole list. Or you could do it the other way around. So this was doing it in a clockwise turn. You could do it the other way around. So you start here, and the next point is here, then here, and so on. Essentially, adjacent indices have an edge between them. Now, we may want to calculate the area of a polygon. And we just pick one starting point. And then we look at the next 2 points. And we sum the area of this triangle. Then we move on to the next pair of adjacent points. We sum the area of this triangle. And the next one. And the next one. Here you see we're overshooting. We're taking some area that's outside our polygon. However, this will be fixed in the next iteration, because then our angle is turned the other way around. Remember, the cross product returns a negative or a positive value. So we subtract what we added in excess. A common problem is to find the convex hull of a set of points. So the convex hull is something you can visualize as if you have your points, a set of points, you take a rubber band and you put it around the points and then you release it. It wraps around the set of points just as needed. So put the rubber band around, it constricts to the outermost points. Now, an algorithm to find this, known as Graham scan. First, you pick the point P0, which has the lowest y coordinate. It doesn't have to be this point. What's important here is that the point is necessarily on the convex hull. And the point which has the lowest y coordinate is bound to be on the convex hull. Then you sort the points by their polar angle with P0. You iterate through all the points. If the current point you're at forms a clockwise angle with the last 2 points, then you pop it from the convex set you're creating. Otherwise, you add the current point to the convex set. The time complexity of this is bounded by the sort, which is O of n log n. So let's do an example. We start at the green point. We sort by the polar angle. So we number them like so. Then add the first 2 values to begin with. And yeah, so if you consider what happens when we add 3, we will have a clockwise angle between 1, 2, 3. So we're gonna pop 2 and then add 3. 1, 3, 4 does not form a clockwise angle, so we just add 4. 3, 4, 5 does not form a clockwise angle, so we add 5. 4, 5, 6 forms a clockwise angle, so we pop 5 and add 6. 4, 6, 7 forms a clockwise angle, so we pop 6 and add 7. Again, 4, 7, 9 is clockwise. No, sorry, 4, 7, 8 is counterclockwise. I forgot the 8. Yeah, so we add the 8 And then next we check, okay, 7, 8, 9, that's clockwise. And we do the same for 4, 7, 9. So slowly we build up until we reach the end. Or reach the start, rather, which is also the end. And now we have a convex hull. So let's see, here we actually do it kind of differently. We sort by x value. Yeah, so in this code we're sorting by x value, and we're going through the indices first left to right, and then right to left. This is simply a different way of programming it. The end result is the same. We store the result in this array hull, and then our function also returns the size here. Another way of finding the convex hull is what's known as the gift tracking algorithm. It's sometimes called Jarvis March. So here we pick the point P0, which has the lowest y coordinate, as our current point PC. And again, it's not important that it is necessarily the lowest y coordinate, it just has to be a point which is definitely on the convex hull. Then we select any point other than our current point. And that will be the best point we have so far. So we say PB is equal to something which is not PC. We then iterate through all the points PI. If PC, PB, PI form a clockwise angle, then PI is a better candidate than PB. So we set PB to PI. So we change what our best point so far is. After iterating through all the points, we add PC to our convex set, and we move to the next best point found. So we set PC to PP. And we repeat these steps until PC equals P0. So until we get back to our starting point. Now, the time complexity of this is O of n times h, where h is the number of points in the convex set. So this depends on the size of our output. Algorithms like this are called output-sensitive algorithms. So their time complexity scales with the size of the output, as well as the input. This can sometimes be better than the O of n log n algorithm, but very rarely, because usually you'll have more than if you have a substantially large set, usually you have more than 20 points coming on the convex hull. However, this algorithm does have some advantages, which we will look at later. So let's do an example here. Again, we start at the point with the lowest y coordinate. We do not sort this time, so they are randomly ordered. So first we just set the next index to the best value. So the orange color represents that. And then we test, okay, can we form a clockwise angle with pi? This is counterclockwise, so it's not better. Counterclockwise, 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 and counterclockwise. Okay, so this is all counterclockwise. And therefore 1 is the best value we found. And we add p0 to our set and move on to the next point. So then 2 is the best value we found so far. And we check, okay, does this form a clockwise angle with p0? It does not. With 3, it does. Okay, so 3 is a better option. So we change the best to 3. Then we check, does it form a clockwise angle with 4? It does, so we move to 4. Then with 5, it does, so we move to 5. And 6, it does not. 7, it does not. So 5 is the best so far. And we add 1 to our set and move on to 5. If you do this again from this point, first you would select P0 and then move on to 2 and then 4. And so you would add 4 to the set. And then 7, 2, and P0 again. And then we have our convex hull. Now, there are other algorithms which exist which solve the same problem. There is quick hull, which is a similar idea to quick sort. There are divide and conquer approaches to this, and some of these can be extended to 3 dimensions or higher. The Graham scan, the n-log-n algorithm I showed you, cannot be extended to 3 dimensions. However, the gift wrapping algorithm can. And the idea is very similar. So if you consider that you are the point P0, what you're doing is you have a field of view here, a 180-degree field of view, and all your points, or all the points, are in your field of view. And what you're searching for the rightmost point, which you can see, and that would be the 1. So after going through all the points, you find this is the rightmost point I see, and then you do the same for the next point. When moving up to 3D, you do the same thing, except you, instead of placing yourself as a point, you place yourself as an edge. So you would find some edge which is on the convex hull, definitely. And then if you place so let's say the edge is PQ. If you place your head at P and your feet at Q, and you look at all the points in 3D space, which one is outermost? Like which is most to the right or most to the left? This is a bit trickier because you need to use something known as a mixed product, which I haven't covered. But it is a product of 3 vectors or 3 points. So you take, if you're finding the mixed product of A, B, and C, you would first take the cross product of B and C and store that in a variable called D. Then you take the dot product of A and D, and that is the mixed product. And this works in the same way as the cross product. So it can tell you whether something is, more to the right from this perspective or more to the left. Yeah, so next problem we should look at is if we have a convex polygon we want to have a simple algorithm to check if some point is within this convex polygon. And the first thing you need to do is just calculate the area of the polygon. Then just check if your point is contained in the polygon. You sum up the area of all the triangles where you select the first point as the point we're checking, and then look at all two adjacent points in the polygon. You sum these areas up together. Just like so. And the total area of these triangles is going to be equal to the area of the polygon if and only if the point is inside. So if you look at this, now we have the same area.
Just as a reminder, what was our formula or method for calculating the area of a polygon?
The cross product divided by 2. So the
Cross of a polygon. Like, let's say, like, I just have the
of the polygon.
The point along the other.
Yeah. Sorry. So we started at a single point, and then we look at the next two adjacent points. And we find the area of this triangle, assigned area. So we just use the cross product for this vector and either this vector or this vector. I would say you do this vector here from this point to this point, and then this vector from this point here to this point here. Okay, and then you move to the next adjacent points. Move to the next. Move to the next. And move to the next. And what's going to happen here is you take this vector here and this vector here. Now it's a clockwise angle. Or sorry, actually this time, yeah, it's a counterclockwise angle. So when you're summing this up, you're going to subtract the thing you added in excess here. So is that clear? Did that answer the question?
How do you know that you've hit that situation that you're summing something outside the polygon?
Here?
Yeah, so how do you know that you're at this case has come up?
The point is you don't have to know. The cross product handles it, because if your vectors, so if you call the first point A here, and the first of the pair we're looking at here is B and then C. You're always going to be looking at the vectors B minus A and C minus B. So for example here, this starts out as a clockwise angle from here to here. So that will give you a negative value. This will also give you a negative value here, a negative value here, and finally here you get a positive value. So if you sum all these values up, you're gonna get the total area of these four together plus the excess here, and then adding the positive number here, you are subtracting from the negative number here.
I see. And so I guess once you've done everything, you take the absolute value of it.
Yeah, at the end you take the absolute value. However, you can use this to determine whether the points of the polygon are in a clockwise or counterclockwise order. Because now you see that we had a negative, 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 positive, and this positive area is really small. So we're going to end up with a negative area, a negative value from the entire area calculation. So this tells us that these points came in clockwise order. If you think, I guess if we did this another way, so if the points were ordered in the other way, we could get a positive value instead of a negative value. So you can determine if the order of a polygon is clockwise or counterclockwise using the area. Okay, so we were at a point in polygon. Okay, so this works if we have a convex polygon. But if it's not convex, how can we do it? We use something called the even-odd rule algorithm. So you examine some ray which is passing through the polygon to a point. If the ray crosses the boundary of the polygon, then it alternately goes from outside to inside. And inside to outside, not outside to inside again. Okay, so if we look at this point and we pick a random ray, doesn't matter which ray. Okay, count the number of intersections with the polygon. So here we have 5 intersection points. Now the ray extends to infinity from one point. So the first intersection is going to tell us, okay, we're in the polygon, and then we're out of the polygon, and then we're in the polygon, and then we're out of the polygon, and then we're in. So because we have an odd number of intersection points, the point has to be inside the polygon. If it's even, then the point is outside the polygon. And like I said earlier, it does not matter which ray we pick. So here again we have an odd number. We have 3. Here we have 4. We are outside. Yeah, there are 2 more things. So we have the closest pair of points, and then I'm gonna show you a demo of one thing. So if we have a set of points and we want to find the pair of points with the smallest distance between them, what we use here is a divide and conquer algorithm. We first sort the points by x-coordinate. We then split the set into 2 equal-sized sets by just, taking the vertical line of the median x value. And everything to the right is in one set, everything to the left is in the other. We solve the problem recursively in the left and right subset. Then at the end we sort the 2 subsets by their y-coordinate. And then we find the smallest distance among the pair of points which lie on the different sides of the line. Okay, now I want to show you something. I don't have any slides with it. There's a really widely used thing in geometry for example, for terrain in 3D worlds. There's a special version of it which is used for self-driving cars. And it's also used to find the point in a point set which is closest to some random query point. So you just plug in a point, and it can quickly tell you, okay, what's the closest point to this point in my point set. This thing is known as the Delaunay triangulation, and I was playing around with it a bit recently. So I'm going to show you how a simple algorithm looks graphically, the steps it takes. So let's see. Okay, so here we have a bunch of points. Can you see this clearly? Like, are the points large enough?
Yeah. Yeah.
Okay. So what we're first going to do is we're going to find a scan triangulation. Essentially, we want to create triangles which make up non-intersecting triangles which make up this point set. So we're going to start by sorting all the points by x value, and then we're going to pass through them, and we're going to add a triangle every time we can. So we're at some current point, we look at the points behind us. If we can add an edge, then we do it. So that means it doesn't intersect with any other edge. So just take a look. This may be a bit too fast. This is what the scan triangulation look like. And now the Delaunay triangulation is going to kick in, and we're going to try to make the picture a bit prettier, essentially. I think it's kind of universally agreed upon that the resulting picture will be prettier. And the property this has is that if you take the circumcircle of any triangle here, then it will not contain any other point in the point set. So I can draw the circles for you. It's going to look a bit messy because there are so many. So these are all the circumcircles. And it's kind of hard to see because we have so many points, but none of these circumcircles contains any point which isn't just the points that form it. And you can get something from this which is called a Voronoi diagram, which helps us with finding the closest point in our point set. So let's remove the circles. Let's turn off the triangulation. Let's draw the Voronoi diagram, or at least mostly. There's some part missing in my code around the edges of the point set. You might notice some, like here. There's no thing separating these 2 points. So we have formed this area here. And all the points within this region are going to have this point as the closest point in the entire point set. What's supposed to happen here is we're supposed to have just a line which cuts between the midpoint of these 2 values.
But I mean, each point is in its own polygon.
Yeah, the Voronoi diagram forms a polygon for each point.
So what's the closest point then?
So if you give this a random point, so say we want to find, okay, we turn out the Voronoi diagram. Okay, what is the closest point to my mouse cursor right now? like where it's pointing right now. Then you use the Voronoi diagram, and you see, okay, I'm within this region here, so it's gonna be this point, because it's the only point that's in this region where my mouse cursor was placed. Now, there's no problem in the problem set which is based on this. I just wanted you to see this so you are aware of its existence, because it has many real-world applications, and it's not limited to only Euclidean distance. You can do Manhattan distance. There's someone that did some other metric which was max distance. So the distance is then the maximum of the y difference and the x difference of 2 points. And then if we add the triangulation on top of this, we can see that like how the polygons of the Voronoi diagram and the triangulation intersect. Or even if you look at the circles, these all have a relation. Maybe I should reduce the set so you can see it clearer. So let's just have 20 points. Oh. Points in total. And then we do a scan triangulation and fix it. It's still a bit clustered. Let's try a bit smaller. Okay, so for example, point here, and point here. That's this large circle here. Note this point here, where it is, the center of the circle. The Voronoi diagram is going to have a point there as well. You can see the circles are all centered around points in the Voronoi diagram. Yeah, I think that's it. So let's look at the problem set. So this time there are 3 bonus problems. There are the 3 here at the bottom. It's pollution solution, sneak attack, and the worm in apple. So this here is a 3D problem. I think all the others, yeah, all the others are 2D. This is the only 3D problem, and it's a bonus problem. The other problems are all 1 point each, and you need 3 problems for full score. sorry, 3 points for full score, which means, well, you also just need 3 problems for full score. Yeah, are there any questions at the end? If not, then we have the problem session coming up. Make sure you register, otherwise you can't submit. And if you can't submit, you can't get a score. Okay, so no questions, so I'm gonna end the stream here.